common phrase in baseball is that the hardest thing to do in sports is hit a round ball with a round bat. With only 4/10ths of a second to react, the hitter is at an obvious disadvantage. It is the role of the pitcher to throw a pitch with the most velocity, change of angle, and change of spin in order to throw the hitter off balance and make him miss or hit the pitch poorly. The four-seam fastball resides in the arsenal of most pitchers. As we watch the ball go into the glove, we can see that there's a lot of backspin on it. This is done because the ball is held across the top two seams, and as it's thrown, the wind is able to catch the ball and rotate it backwards, creating the highest amount of velocity possible through spin that keeps the ball up in the strike zone. The job of a curveball, whether it's an overhand curveball which drops down or a sidearm curveball which slides to the side, is to give the hitter an impression that the ball is going to land in a certain place when in fact it's going to move to another. There are many different ways to hold a curveball, but as the pitcher holds on the seams or around the seams and throws it with a cock of the wrist, it spins in a certain way, as we can see, that the ball catches an amount of air on its side and is pushed downwards.
With a knuckleball, since the rotation of the ball is ever changing, the forces of air and the wake behind it do so as well. If it's staying still, the airflow will be constant on both sides of the ball, but as it jets one side, it'll act like a curveball. As it jets to the other, it'll act like a fastball, and this is what gives the knuckleball its randomness and difficulty to hit. So Jake is actually 642 inches away from the plate when he releases the ball. Now, upon reviewing his pitch over and over at normal speed, he gets his pitch there when it releases its hand to the plate in 0.6 seconds. So 642 over 0.06 equals x over 1. And we're going to determine how many inches per second the ball goes by using a calculator. 642 divided by 0.6. Using the acceleration we found in the last equation, we were able to plug in the numbers to F net equals ma times this number here. The net force on the ball comes out to be 2.06 newtons. X turns out to be 28, thus 2 over 28 equals 1/14 of a second for my arm to release the ball. As I measured that with a string later on, it turns out to be 40 inches, which comes out to be exactly 1 meter. So it goes 40 inches in 1/14 of a second. It comes out to be, when you times 14 by 40, it becomes 560 inches per second. And that becomes, this number here translates to 14.224 meters per second. And that's our acceleration. The first thing we're going to calculate is the net force on the ball, which is found by the equation F net equals mass times acceleration. The mass on the ball, which I found by looking online, is 0.145 kilograms on average. The acceleration I found by using the camera frames per second. We filmed at 420 frames per second, and in real time is 30 frames per second. It took 2 seconds for my arm per second, and in real time is 30 frames per second. It took 2 seconds for my arm to go from here to here and release the ball. So I needed to know how many seconds it took in real time to get that motion. This x turns out to be 28, thus 2 over 28 equals 1/14 of a second for my arm to release the ball. As I measured that with a string later on, our next task was to determine the velocity of the baseball. So from mound to plate, it's 60.5 feet, which translates to 726 inches. Now, with the stride of the baseball, as shown in previous videos, you don't actually throw the baseball from 60.5 feet. You actually step forward and release it much farther towards the plate. So with Jake's height in mind, Jake is exactly 73 inches tall, and on average, major league pitchers throw 15% more than their stride. So 73 times 1.15 equals 84 inches. So Jake is actually 642
X
inches,
equals
1,070 inches per second. When divided by 12, the answer comes out to be 89.16 feet per second. And with a converter, that turns out to be 27.18 meters per second.